for topic 5 this time, actually forget the PowerPoint. We're just going to use the PowerPoint. If you want to play through this again later, is totally fine for the setup, but we are just going to go ahead and start with the database this time and do it all in SQL Server. So we have now a terrible query. This is not a good query. I mean, as we've said, this table is not a good table, right? It's both normalized and denormalized. And look, we're even returning both of those in the query, right? The truth, though, the truth about queries in the real world is that they're often terrible. And just because, I mean, it's not because like people are stupid, it's just because sometimes people need to do things that SQL Server isn't that great at. And sometimes long ago, someone made a mistake in designing our table and included all of these weird columns in it. So imagine in this case that we have, this table has this inevitable lob column in it because, let's see if I can zoom out, because maybe this is like a notes field, right? So imagine we have this table where we get one row for every baby that's born and named in the United States. Presumably, if a baby doesn't get named quickly, they don't get a row, right? We maybe only get the row once the baby has a name, I suppose. Not sure how that would actually work. But we have this notes column, and the note might be really extensive, right? The note might be, so it's made as this really long column, and they decided to put it in the table itself. The column does allow nulls on the table. Let's actually open up the table and look at the table here, right? So looking at our table, we are in this copy of the Babby Names database, and we're in first name by birth date 2000 to 2017, and here is inevitable lob column. A little wider there, right? So it does allow nulls, but it can be really long. And when it's in a large object column like this, when the column is really long, it can be stored off page. Like if it doesn't fit on the 8K page, SQL Server can actually store it off page. Sometimes our internal people need to search this column for just specific notes, right? So they need to use queries like this that say, I want to look for anything where these characters are anywhere in the column. And this is really difficult to index because all of our indexes do things like, okay, if we've got a name and I'm alphabetizing by name, right? I'm looking at the beginning of that word. I'm not alphabetizing by the middle of a word. If I'm creating an index on a character column, everything is about the very beginning of the character column. So if I'm looking for something in the middle of it, my non-clustered index isn't really going to help me say where is nom somewhere in there. So this query took us 17 seconds. Now this first run of the query, I was having to pull in data from disk. So let's run it again. I'm going to run it again, this time with statistics IO and time on, and we're going to baseline this now that the data is in memory and see how long it takes then. We don't currently, if I'm looking at the indexes on this table, we only have the clustered index, which is on that unique identifier column there, right? That doesn't help us find characters in inevitable lob column at all. So, okay, this time it was a little bit faster. Before we index it at all, we are at 38 seconds and a half seconds of CPU time, 12 and a half seconds of elapsed time, and we have 522,000 logical reads. We can see, by the way, the number of lob logical reads. So data stored off on these extra large object pages, we had to read 91,000 of those. That was data that didn't fit on the 8K pages and was put off to the side on these linked large object pages. We had to read a bunch of those. Looking at our actual execution plan, we will see that at this point, the only option the query has is scan the clustered index. That's all we've got is a clustered index. It does have the option on whether or not to go parallel, but we don't have a lot to do with that. This query does decide, we are doing an order by here. So the query decides, okay, the best way for me to do this is I'm going to scan this clustered index. There's no predicate here at all. Our predicate is on the lob column, and our predicate is being put in a separate filter. It is a parallel filter, but everything goes into this filter, and then the filter is where we have the predicate. The optimization to suck this filter in and put it as a predicate on the clustered index scan, that optimization doesn't work with lob columns, so we see it as a separate operator. Then it knows, hey, I'm probably not going to get very many rows back that match this pattern, just guessing, right? It did guess 1800. There were actually 0, but it's going to put all those into a sort operator and then return them back. So we are not going to be able to do very well with this, but your challenge is, what is the best that you can do with this really ugly, really awful problem? What in SQL Server is the best you can do? And it may not be very good, right? But is there a way that we can help this awful query, which is difficult to optimize in SQL Server? Any ideas about the ways we could do this? And actually on this one, let's go ahead and skip the break. And if you've got any ideas, just throw them in the chat room as I switch on over to the solution for this one. The red herring, I'll talk through the red herring as you think about this. The one that we might be tempted to think would help for this is called full text indexing in SQL Server. Full text indexing is a separate kind of indexing. We've had it since SQL Server 2005, I believe. We've had it for a really long time. And it helps if we have a phrase in there. So I might have a notes column, you know, maybe it says the red fox jumped over the lazy dog or something like that, right? Full text indexing will take that sentence, is it quick red fox jumps over the lazy dog? The full text index will take all those different words like fox and lazy dog, and it will index those individual words. So I could say, oh, I want to find all of the comments that talk about fox. And full text indexing would help with that. It also can help with leading words, like jumping, like say jumping was in my phrase. I am jumping over the lazy dog. I could search for the word jump, and it would be like, oh, jumping is a form of jump. You should find this one. It would be good at that too. But the gotcha with full text indexing is that it really likes prefixes. And it's smart about certain things. It's really designed for this whole thing about phrases. I want to find phrases like this, or I want to find words like this, but it's thinking about words, not just strings of characters. So I could find words starting with something like jump, jumping, jumped, that kind of thing. I could find, I could ignore stop words and different phrases. I could do lots of things with language, but it does not help with leading wildcards. So in my case, I want to find nom with this leading wild, nom could be jump. I could have German words in there, and nom is like at the very end of the word. It's not going to help me with this. It's not what it's designed for. It's designed more to be words and phrases, parts of words that are the leading parts or variations of words, things to do with dictionary and natural language. So full text indexing is not the solution for this. Devin has a suggestion, possibly a filtered index. Aha, a filtered index. Very, very interesting. Well, we might try this. We're going to get to filtered indexes. Good guess. We're going to get to this. We might just try. Okay, I'm going to create an index on inevitable lob column. Yeah, I'm not going to be able to seek on it, but at least I could scan it. But we cannot put varchar max columns or other large object columns in the key of our index. We are not allowed to put, they can't, they don't make sense in terms of that tree shape that we want to create, right? So we might try that. It's going to be, it's not going to happen. So we might say, okay, and I'll go ahead and start this one. Okay, I'm going to create a different, I can't put inevitable lob column in the key of the index. I can't put it there. I'm not allowed to. So I'm going to put fake system create date time in the key because I have to have a column in the key. I have to have at least one column in the key, and my query is ordering by that column. So it's going in the key because I have to have a column in the key. And then I'm going to put inevitable lob column as an included column. I can put large object columns as included columns. Now, this is not necessarily a good idea. Just because we're allowed to put large object columns in the included columns, it doesn't mean it's great, because imagine if I Well, I do have a fair amount. I have a little bit of data in here. Not a lot of rows have this. This is one of the things, is not a lot of rows have notes. But when remember how I did have those lob pages read, those extra lob pages read that are off page. So now on my base table, I have an index tree for my clustered index, and my large object pages, when they wouldn't fit on row, they're all off row. The same thing is going to happen in my non-clustered index, where I've got lob pages that are off row when they don't fit into the pages for the non-clustered index. So to find them, I've got to go for everyone, go off row, find the lob. It's just like, is that really awesome? Well, let's see. We're going to see how awesome or not awesome it is. So I have now, by the way, I didn't do with online equals on again. I'm going to see if I can catch it this time. I'm going to do SP who is active. This is a free procedure from Atom Mechanic. You can get it at whoisactive.com. And I'm going to do this with getLocks equals 1. So this is the free download for where Atom published this, just to look at the locks that the create index is holding out. So we can look at the lock graph for the create index. It's still running, so we aren't wasting time there. And we can see that on the first name by birth date 2000 to 2017 table, we have a schema modification lock on the Hobbit stands for heap or B tree structure. We have a shared lock on the object itself. We have an exclusive page lock right now. Basically, what will happen is, while this is creating, modifications will be blocked, which then can block a lot of read operations. That's in even in Enterprise Edition, right? So if we really want to maintain access for the table, we want to say, create it with online equals on. Even then, at the very end of the index create operation, it is going to briefly have to get an exclusive lock as it updates the metadata to say, hey, I have this new index there. So you can have blocking even with online equals on, but we are going to take out more locks in Standard Edition or in Enterprise Edition if we don't say it with online equals on. That was just a bit of geeking out while we were waiting for it to create, because it took 3 minutes. So it took 3 minutes because if we want to look at how big this index is, looking at sys.dmdb partition stats, our non-clustered index, here's this index ID 1 is the clustered index of the table. Our non-clustered index is almost as big, right? Our table is over 4 gigs. Our non-clustered index is like 3.3 gigs, and they each have the same amount of large object pages, right? So I have created an object nearly as big as my table itself. Will my query use it? Well, it will use it, but it's not particularly fast. So 6, 7 seconds, right? And I had to create that big index, which is now going to take up space in memory whenever it's used, take up space in backups. And there are no rows for NOM, by the way, right? So we've got 404,000 logical reads. Now, I didn't have my actual plans on there. I'm going to do just estimated plan, just so we can see. Yep, we are using non-clustered index inevitable lob column. Kind of a bummer, right? So we're going parallel everywhere. Yeah, it's kind of a drag, right? So it is using the index, but it's not that good. So let's add the filter on. So this time I'm creating the index, same key column, same included column, but I've said where inevitable lob column is not null. In our case, inevitable lob column, it can have really long values, but it just isn't on a very high percentage of the rows. So if I want this index to not take up 3 gigs of space, a filter can be really, really useful here. So let's now look at the size of this index. The filter has taken that way, way down. Yeah, I still have the same amount of data on those large object pages, but the structure itself that points to those pages is much, much smaller because I just have not included the massive amount of rows that don't have a note on them. I do have a note on like 18,000 columns though. So the filtered index in this case has taken the, I mean, it's a questionable practice. It's generally not a good thing to include a large object column on an index and create copies of all those lop rows. But in the case where it's a pretty selective query and we can use a filter to say, okay, we're just making those pages really easy to get to. Yeah, we are creating a copy of them, but we're at least able to do it in a small index. It makes that practice much less questionable. So will our query automatically use the index, right? So our filtered index, one of the pains with filtered indexes is that often you have to match the filter column literally to get SQL Server to use the index. So oftentimes you have to really make sure your predicates match perfectly. I do not have, I have where inevitable column is like nom. I don't have where it's not null in the query. One of the nice thing about is not null in indexes is that this will match to it, and I don't have to add that criteria in the index. Now you may have noticed this query did not come back right away. It's like, oh yeah, that's not fast, is it? Okay, let's look at the execution plan. Did it use our index? Our index is still named IX inevitable lob column, which is a terrible name. It's a terrible name. And we are using it. We are using that filtered index, but our query is still slow. And in fact, our query, yeah, it's what, 13 milliseconds now. What was our starting one? So when we started out, and we can remeasure this at the end, let's go ahead and I'm going to run it again just to make sure that the data is in cache. But it may actually have gotten a little bit slower because now our query is going single threaded. Right? When we started out, it was actually using parallelism on all of the operators, including the filters. By giving it the cheaper index, it's now just using one little CPU, but that means that our CPU time and our lapse time are now pretty much the same. But I think they actually are close. I think they're pretty close to what we started out as. So we are only doing, though, 194 reads, right? Because it can find these rows really easily because of the filter now. We're doing 91,635 lob logical reads though. So the query isn't faster. And the reason the query isn't faster is that checking these long string columns, okay, is nom anywhere in there, is just not something the SQL Server is great at. It takes a long time. But by creating the filtered index, we have reduced the amount of times that we have to scan the base table itself. So we're not going to have as many issues with locking and blocking if we're using pessimistic locking. We've reduced the amount of CPU we're using. So we haven't been able to really make it better for our customer in this case because the SQL Server just isn't very good at this. But we at least are not as likely to impact other customers who are running queries at the same time this is running because we're not scanning the whole table into memory and maybe, hogging all the memory. We're not taking out a ton of locks as we traverse the table. So we've kind of done less harm by allowing a terrible query to run. I know it's really, maybe I shouldn't close the first day on this one because I'm like, it's kind of a downer. So we've made it better. I mean, we could try to do other things. So we could try to add data compression as page to this. One thing about data compression, it doesn't apply to lob columns. So we can do this. But all that we have compressed, if we look at how big the index is, all that we have compressed is the small amount of data that is on the B tree. It isn't going to really change our performance in a notable way on this time because it just hasn't compressed the lob columns. Let me go back up and actually just show that the query takes the same amount of time. So that's not necessary. It's not going to slow it down in this case, but because it hasn't compressed the lob columns, it hasn't really changed anything. There are some interesting, and I'm going to go ahead and scroll down. There are some interesting new options in SQL Server 2016 and higher. So that took 14 seconds that time. There is now a compress function in T-SQL. So compress essentially is like zipping up your data like the zip command would do. And compress always outputs the data type var binary max. So you have to store the data in a var binary max column, and you have to use the uncompress function when you're pulling the data out. So if we wanted to use it in this, here's a little bit about what it would look like. I'm going to, just for speed, I'm creating a copy of the table named Same thing, but then compressed. And what I'm doing is I'm using the compress function to create a column named inevitable lob column compressed. And the beauty of this is that it can compress large object types. This could take up a lot less space on disk. It's not really going to be amazing for this scenario, but imagine that I had a lot of large object data that I needed to put in a SQL server for some reason, and I was really going to read it very rarely, but I really had to have it in there for regulation purposes or compliant purposes. This could help that take up a lot less space. So on my new table, I'm going to add a clustered index, and let's look at how much space the lob column takes up now, right? So it was able to compress that down a lot. Now I'm not going to be able to index this super well at all, right? Because the same limitations I've had with indexing applies. The cool thing is really just that it takes up less space. If I want to query this, I have to change my query. I have to decompress the column and then change the data type because it's var binary right now. So I have to, if I want to return it, I have to change the data type. So I'm doing the same thing in my predicate here before I do the comparison. Right, so it's still going to be slow. Still going to be slow, but it's slow, but I'm taking up less space, which in some cases may be what you prefer. Like it's going to be slow either way if I put it in the SQL server, but if it's okay that it's slow, and this, notice it is 15, 16 seconds, it's still slow, maybe it taking less space is the lesser evil in some cases. So it's an interesting option in SQL Server 2016 and higher. I do have a little warning there about memory grant usage, but it was able to do it. You can you can index these compressed columns. They're just var binary max columns, so you can put them in, I mean, they're large objects, so you can only put them in the includes if you need to. You can put them in filters, but this time, now that I've monkeyed around with this and I've used the var binary max, if I'm doing this comparison against them, this is how you can tell if a filtered index that, well, not actually, no, this is not how you, this is one way you can tell if a filtered index isn't used. I tried to force it on here with, if you try to force an index and it can't use it properly, safely, you will get a failure too. Let's hint this out. What I thought I was going to show you, because I hadn't noticed the index hint, if I use a query, if I run a query and there's a filtered index that it doesn't think is safe to use, like it's not picking it because it's worried that the index may not completely match. And in this case, the index doesn't match completely because of all this cast decompress stuff. You'll get this little warning that says, something wrong. There's another warning in here. We're going to go into the, so only one warning will show in those properties. There may be other warnings. If we go down here into warnings, are you not showing me my other warning? Yeah, so it's doing a clustered index scan. It's not, oh, SQL Server, I'm so disappointed. I thought you were showing me. So it won't always show you the warning. That's so sad. Sometimes it should show it. It should show an unmatched indexes warning. And sometimes you will get an unmatched indexes warning, and it has the text unmatched indexes, and it says, I couldn't use this index, possibly a filtered index, because it wasn't safe to use. I thought they'd fixed issues where that warning didn't show up, but apparently this is one of the cases where oh, sad, I should file a bug. If I do add, in this case, if I add inevitable lob column compressed is not null and blah, 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 it will be willing to actually use my index. So I do still have that functionality. So to wrap up, and there are slides for this too, we're just not going to step through them. There are some queries that are very, very difficult to index. Indexing doesn't get us around problem queries like queries that are, and now I'm scrolling up to see the index, queries like this that have what's called non-SARGable predicates. Non-clustered, clustered indexes in SQL Server, SQL Server can't seek on these based on the way that indexes work. And this leading wildcard means that even full text indexes aren't great for this. So these are really challenges, right? It's not just that you don't know what index to use, it's that SQL Server isn't great at this because this is not a seekable predicate, right? This search argument, the non-SARGable word, that stands for search argument, this is not an argument that can effectively be searched on. We can limit some of the pains from that sometimes by creating an index where we can, in this case, like a filtered index, we limited the amount of data that had to be scanned so that we saved some memory, we saved some locks, we saved some CPU usage, but the query still didn't end up being super fast, right? So there are limitations to what we can do. Now, the good news is when we start out tomorrow, we get to start out with a way more fun case of an index that does make things awesomely faster. Sometimes we can just sort of limit the trouble, but tomorrow we will get to make a lot of stuff faster.